Honors Chemistry. This is Lesson 18 on Solution Stoichiometry. Alright, so stoichiometry is a really important topic, so we spent quite a bit of time in this class on it. And there's different types of stoichiometry, different ways to approach it depending on what you're dealing with, what kind of substance and what state that it's in. But the thing they all have in common is you have to come out with some number of moles, that is, number of particles. So in the equation below, it takes one molecule of CH4 to match up with two molecules of O2 to produce a molecule of CO2 and two molecules of H2O. So chemical equations count numbers of molecules or particles in general. So what we're dealing with, what we usually talk in terms of is moles, which is a large number of these particles, 6.022 times 10 to the 23rd power. So you have to have everything in terms of numbers of particles, of molecules, atoms, whatever, ions. And so that's what a mole is. So we have to get things converted into moles. So we spent a good number of time on grams to moles. That's the first column there, the first yellow arrow you see there, making grams to moles conversion. Then we spent a little bit of time on gases. These can be unknown gases where we calculate the moles of the gas based on the pressure, volume, and temperature of the gas. Now we're moving into solution stoichiometry, and a solution is a mixture of two substances, a solute mixed in or dissolved into a solvent. So think of lemonade mix being mixed into water. That's a solution. So we have to, since you have two things mixed together, we have to have a slightly different way of calculating how many moles. And so that's what this lesson is going to deal with. So there it is. We're focused on that third one. The main measure of concentration, which is how much of the lemonade mix you have mixed into the water. High concentration would mean the lemonade is really strong. Low concentration would mean it's really weak. Or more generally, how much of the solute you have mixed into the solvent. We usually measure that in something called molarity. There are other measures that we will learn about, but molarity is the main one that we're going to use in these problem sets. So to get moles from molarity, you would have to take the molarity, which is moles per liter, how many moles of the solute per liters of the solution, and multiply by the number of liters of the solution, and that will give you the number of moles. So solutions are a mixture of two substances. Solutions, there are three terms you need to know when dealing with solutions. So the solute. That is the smaller amount that is dissolved, and it's the shorter of the words. That's why I put the number of letters there. It's 6 letters long. The shortest word has the smallest amount. That's the solute. In our lemonade example, that's the lemonade mix. That's the powdered lemonade mix. You just take a couple of scoopfuls of that and you mix it into water. The water is the solvent, and that's 7 letters long. So there's more water than there is lemonade mix, and solvent is a longer word than solute. So more than the amount of solute, and a longer, so the solvent is more than the amount of solute, and it's a longer word than the word solute. Just a little way to remember it. Finally, if you put them both together, that's what you have the most of. That's called the solution. And the solute, that's the solute and the solvent together. And that's the greatest amount, and it has the longest word. So that's just a way to remember which is which. So example, when lemonade powder is mixed in water, the powder is the solute, should be the powder is the solute, and the water is the solvent. The powder and the water together make the solution. So just kind of fix this image in your mind of the three. What the solute is, what the solvent is, and then the solution is the two of them mixed together. Okay, so molarity. The ratio of the solute to the solvent or solution is called the concentration of the solution. Measures of concentration state the ratio of solutes to solvent or solution. There are several ways to measure concentration. Molarity is the most common that we're going to use in this unit. Molarity measures the moles of solute per liter of solution. So moles of solute over liters of solution. It's not liters of solvent. It's not just liters of water. It's the liters of the two mixed together. It's the lemonade powder and the water mixed together. It's liters of solution. So moles of lemonade powder over liters of the solution when they're mixed together. Molarity is represented by the letter capital M. Molarity is the most common measure of concentration we will use in this class. Alright, so let's take a look at an example here. So the ratio of solute to solvent or solution, depends on which measure of concentration you're using, is called the concentration of the solution. Measures of concentration state the ratio of solutes to solvent or solution. There are several ways to measure concentration. Molarity measures the moles of solute per liter of solution. So let's take an example here. What is the molarity when 8.9 grams of lithium is dissolved in water to create 550 milliliters of solution? Alright, so you'll notice one thing about this problem is you're given two numbers in the problem. We're used to only seeing one number, and that's going to be one factor that's going to make the problems a little more complicated, but once you get used to doing them, it won't seem that much more complicated. Okay, so you have two numbers here. So the first thing you want to ask is, what is molarity? Okay, they want to know what the molarity is, but what is molarity? So what you have to do is whenever you're asked for molarity, you need to break it into that ratio up above that you see. It's moles of solute over liters of solution. Don't just leave it as molarity as capital M in your equation. You won't be able to solve the problem. You need to find some number of moles of solute over liters of solution. So the first thing we do is it's asking for molarity, so that's moles. In this case, the solute is lithium. So it's moles of lithium over liters of solution. SOLN is abbreviation for solution, and it's simply the lithium and the water mixed together. But rather than write Li plus H2O or something like that, just write solution. It's the lithium and the water mixed together. Okay, so that's what you're looking for. Now, what are you given? This is a little more complicated. First of all, you notice that answer is going to have two units of measure. It's going to have one on the top and one on the bottom. We haven't seen that before. We've only seen an answer in either moles or grams or liters or something like that. Now you've got moles per liter. All right, so now what about what we're given? We're given two numbers. So you're going to create those as a ratio. So 8.9 grams of lithium over 550 milliliters. So in that solution, there's 8.9 grams of lithium mixed into enough water to create 550 milliliters of solution. Not 550 milliliters of water, that's the solvent. It's 550 milliliters of the two of them mixed together. So we have two levels in this problem. So you treat it like two separate problems, the top part and the bottom part. So you convert grams to moles. So look at the top part only, the numerators only. You have 8.9 grams of lithium. You need to end up with moles of lithium. So you've done this conversion 100 times in this class. It's a moles to liters, it's a grams to moles conversion. Okay, so what you need for that, as you know from doing this a lot of times, is the molar mass of lithium. Next, once you've taken care of that, you need to convert the milliliters in the 550 milliliters of solution to liters of solution. So you need to go from milliliters to liters. That's a very common conversion that you'll have to do in these types of problems, because oftentimes your volume is given to you in milliliters, but molarity is expressed in liters. So you have to convert from milliliters to liters. That happens a lot in these problems. Okay, so let's rewrite the problem here. There's the same problem, okay, and the same setup that we had before. So again, we have two levels. Convert grams to moles on the top, convert milliliters to liters on the bottom, and there's the conversions that you're going to need. It's 1 mole of lithium equals 6.94 grams of lithium. That's the molar mass conversion for lithium. You've done those many times before, and you get that off the periodic table. And then liters to milliliters, there's a standard relationship. It doesn't matter what the substance is. 1 liter equals 1,000 milliliters. So you're going to need that to make the conversion on the bottom. So deal with the top and bottom conversion separately. So we're going to go ahead and start with the top. You have the molar mass down there in the lower left, so you need to have one of those on top, one of those on the bottom, just like you've done many times before. Which one has to go on the bottom? Convert grams lithium to moles lithium. So the grams of lithium has to go on the bottom because you need it to cancel out with grams of lithium on the top. The 8.9 grams of lithium has to cancel out. Okay, so now you have moles of lithium on the top, and that's what you want in your final answer. So you've taken care of the top. You're done dealing with the top. You've done the only conversion you needed to do. Now you need to go to the bottom, and that's to convert milliliters to liters. And the conversion is 1 liter equals 1,000 milliliters. So which one do you want on the top and which one do you want on the bottom? You need the milliliter solution over there where the 550 is. You need that to cancel out. And you need liters of solution to appear down there on the bottom. So 1 liter, 1,000 milliliters, which one goes on top, which one goes on bottom? Think about it. So the 1,000 milliliters solution goes on top, the 1 liter solution goes on the bottom. Now, even though this relationship of 1,000 milliliters equals 1 liter is true for any substance, you still want to put the substance next to it. It's always unit of measure and what the substance is. In this case, the substance is the solution. It's the mixture. The reason is because you might have milliliters of some other substance or liters of some other substance, and you don't want to accidentally cancel the wrong substances. So it's got to be milliliters of solution that gets canceled. So we go ahead and do that. So the milliliters of solution on the lower left cancels with milliliters of solution in the conversion, and the only thing you have left on the bottom is liters of solution. So that's what's going to go into your final answer. So you notice this wasn't a nice sequence of going from left to right with the cancellations the way it's always been before. You had to kind of, juggle your cancellations a little at different places here. So anyway, you'll get used to doing this with practice, all right? So now we have the units of measure set up correctly. So we simply have to say 8.9 times 1 times 1,000 divided by 550 divided by 6.94 divided by 1, and that gives you 2.3 moles of lithium per liters of solution. But it is a molarity, that is molarity, so you usually write it as 2.3 capital M. 2.3 capital M, and that would be your final answer for this problem. Okay, so just go ahead and write this problem out. Literally write it out on a piece of scratch paper a couple times. Be sure you understand how the cancellations work and that you understand the concept, because now you're dealing on 2 levels, not just a single level when you solve these types of problems. Okay, now we move on to another measure of concentration called molality. The ratio of solute to solvent or solution is called concentration of solution. Measures of concentration state the ratio of solutes to either solvent or solution. There are several ways to measure concentration. Again, I'm repeating this because I really want to, grind these definitions into your head and what we're talking about here. So molality measures moles of solute per kilogram of solvent. So it's easy to confuse this with molarity. They're only different by 1 letter in their name. They both have moles of solute on the top, but molarity has liters of solution, whereas molality has kilograms of solvent. In other words, if it's mixed in water, the kilograms of water, that would be H2O. Molality is represented by small m, lowercase m. Notice that the denominator is kilograms of solvent, not liters of solution, the way it is with molarity. Molality is independent of temperature because kilograms of solvent does not change with temperature. Liters of solution changes with temperature. Think about it. If you have a liter of water and you stick it in the freezer and it freezes, it's going to expand. You may have seen that before. It might even, if you put it in a glass, it might even break the glass. It expands by about 10%. So liters, the number of liters you have, depend on temperature. If it's ice, then the liters, it's going to be more liters. It's going to expand out to more liters than it was as liquid water. Therefore, if the liters can change with temperature, that means the molarity can change with temperature because it's based on liters of solution. With molality, that's not true. Kilograms of solvent, let's say kilograms of water, it doesn't matter whether you have liquid water or ice. That's expanded water, that's frozen expanded water. It doesn't matter. It's going to still weigh a kilogram. It doesn't add any mass just by expanding. It's just the molecules have spread out more. So molality does not change with temperature, whereas molarity does. Okay, so mass percent. So the ratio of solute to solvent or solution is called the concentration of the solution. Measures of concentration state the ratio of solutes to solvent or solution. There are several ways to measure concentration. So mass percent measures the grams of solute over the grams of the solution. So it's grams over grams, so the grams are going to cancel out. And you multiply by 100%, or multiply by 100, then put a percent sign, and that'll tell you what percent of the solution is your solute. And you can't have more than one solute, by the way, so you'd have to add up everything. But in this case, let's just say we're talking about lithium dissolved in water in the earlier example. Then it would be the grams of lithium divided by the grams of the lithium plus the water. Both of them together, not just the water and not just the water. So lithium, grams of lithium over grams of lithium plus grams of water. The grams all cancel out, so it has no dimensions to it, and you multiply by 100 times percent. And that's called a mass percent. Mass percent is represented as a percentage, and that's it. Mole fraction. So again, the ratio of solute or solvent to solvent or solution is called the concentration of the solution. Measures of concentration state the ratio of solutes to solvent or solution. There are several ways to measure concentration. Mole fraction. Mole fraction sounds kind of like mass percent. It measures the moles of a solute over the moles of the solution. So you take the moles of the solute and divide it by the moles of the solute plus the moles of the solvent. That's both of those together will be the moles of the solution. So it's kind of like mass percent, except you're dealing with moles, not with grams, and you don't multiply by 100%. Mole fraction is used a lot in gas law problems, and we'll see some of those later on. Okay, so mole fraction is represented by the Greek letter chi, which is chi. It's spelled C-H-I, it's pronounced K-I, chi. So that X-looking letter is the representation for mole fraction. Mole fraction is often used in analysis of gases. Parts per million. So again, the ratio of solute to solvent or solution is called the concentration of the solution. Measures of concentration state the ratio of solutes to solvent or solution. There are several ways to measure concentration. Parts per million is computed the same way as mass percent. You use grams, except we multiply by a million, not by 100%. So it's grams of solute divided by grams of solute plus grams of solvent. That's what grams of solution is. So everything mixed together. And then you multiply by a million. Parts per million is represented by the abbreviation ppm, parts per million. Parts per million is used when concentrations are very small, very, very small, such as the amount of lead present in drinking water. So there are toxins in the drinking water that come out of your tap, but scientists know and doctors and biologists know that as long as they're below certain levels, they won't have a bad effect on your body. So there might be, for example, 3 lead atoms for every 10 million water molecules. So that would be measured in parts per million because it's a very, very small concentration. So instead of multiplying by just 100, you multiply by a million. There are also parts per billion. You would multiply by a billion, and even parts per trillion. You would multiply by the whole thing by a trillion. Okay? All right, density. Density is the mass of a substance divided by how much volume it occupies. Density is represented by lowercase d or the Greek letter rho. It looks like a scripted P. It's pronounced rho. It's a Greek letter. We're going to use d because it makes more sense to use d for density. Density is measured in grams per liter. So grams is an amount of mass and liters is an amount of volume. So it's how much mass you have packed into a certain amount of volume. So you could have a cotton ball that's fairly large, and a steel ball that's fairly small, they might have the same mass. If you put them on a scale, they would weigh the same. But the steel ball is more dense because its matter is packed into a smaller volume. So it's said to be more dense. So example, the density of magnesium equals, now this is not a number that always applies to magnesium. I'm just using an example here. But the density of magnesium equals 15 grams per liter. That can be written as a conversion factor that we've used in this class. 15 grams of magnesium equals 1 liter solution. In other words, if you're going to write a conversion factor and your ratio for a problem, for a stoichiometry problem, you're used to seeing the equation the way you see it over here on the right. But you may see it in the problem written like this. So you should understand that 15 grams per liter means 15 grams of the solute, that's magnesium in this case, equals 1 liter of the solution. That would be magnesium plus water mixed together would be the solution. I'm going to have you do some exercises on this so that you can practice recognizing the relationship between these two. Okay, so learn to recognize measures in both expanded and short form. These are terms that I invented here for this because I want you to be sure that you know what you're seeing if you're doing a problem and you see a number that you don't quite recognize. Let me just give you the examples and you'll see what I mean. Expanded form is the form that we have used for molar mass. So you've seen this 100 times in this class. 1 mole of O2 equals 32 grams of O2. But in a chemistry book or a problem on a standardized test, they won't write it out that way. They're going to more likely say the molar mass of O2 equals 32 grams per mole. So you should recognize that 32 grams per mole is the same as saying 1 mole of O2 equals 32 grams of O2. What you're really saying is 32 grams of O2 for every 1 mole of O2. And you can flip that ratio. You could set up the ratio 1 mole of O2 over 32 grams of O2 or 32 grams of O2 over 1 mole of O2. But just recognize that what you're seeing in the short form is the way it might appear in a chemistry problem. So you should know what to do with that. Here's another one. Same thing. So 1 mole of silver equals 107.87 grams of silver. So you could write that as the molar mass of silver is 107.87 grams per mole. Those are saying exactly the same thing, so you should recognize that. Finally, here's one for density. 11.9 grams of bromine equals 1 liter of solution. And what that's really saying is that the density of bromine is 11.9 grams per liter of solution. So when you see 11.9 grams per liter, you can change that into 11.9 grams of your solute, bromine, equals 1 liter of your solution, which would be bromine plus H2O, plus water mixed together. Solvent in this class is always going to be water. It's always going to be H2O in this class, unless otherwise stated, but that almost will never be stated. Okay, so you'll see examples of these, and we'll deal with them when we see them in actual problems, okay? All right, so that is everything for this lesson. So the problem set is for this is lesson 18 is really 2 assignments put together in one. So it's kind of long. It's not due until Monday, the 26th of April. So go ahead and get started on it now because you will be given another shorter assignment on Wednesday. That's our only other class this week to do that. Okay, so we'll see you in class.